by slowing runoff. Strips of grass or cover crops such as hay slow runoff even more and act to promote water infiltration and trap sediment. Crops on a farm in northeastern Iowa are planted to decrease water erosion. Figure 6.25 Soil conservation. Creating grassed waterways is another common practice. Natural drainageways are shaped to form smooth, shallow channels and then planted with grass. The grass prevents the formation of gullies and traps soil washed from cropland. Frequently, crop residues are also left on fields. This debris protects the surface from both water and wind erosion. To protect fields from excessive wind erosion, rows of trees and shrubs are planted as windbreaks that slow the wind and deflect it upward. Grassed waterway on a Pennsylvania farm. Figure 6.26 Reducing erosion by water. Windbreaks protect wheat fields in North Dakota. Did you know? Figure 6.27 Reducing wind erosion. In the United States, it is estimated that the amount of soil annually eroded from farms exceeds the amount of soil that forms by more than 2 billion tons. Concept checks 6.7. 1. Why are soils in tropical rainforests not well suited for farming? 2. Place these phenomena related to soil erosion in the proper sequence: sheet erosion, gullies, raindrop impact, rills, stream. 3. Explain how human activities have affected the rate of soil erosion. 4. Briefly describe 3 ways to control soil erosion. 6.8 Weathering and/or deposits. Relate weathering to the formation of certain or deposits. Weathering creates many important mineral deposits by concentrating minor amounts of metals that are scattered through unweathered rock into economically valuable concentrations. Such a transformation, termed secondary enrichment, takes place in one of 2 ways. In one situation, chemical weathering coupled with downward percolating water removes undesired materials from decomposing rock, leaving the desired elements enriched in the upper zones of the soil. The second way is basically the reverse of the first. That is, the desirable elements that are found in low concentrations near the surface are removed and carried to lower zones, where they are redeposited and become more concentrated. Bauxite. The formation of bauxite, the principal ore of aluminum, is one important example of an ore created as a result of enrichment by weathering processes. Although aluminum is the 3rd most abundant element in Earth's crust, economically valuable concentrations of this important metal are not common because most aluminum is tied up in silicate minerals, from which it is extremely difficult to extract. This ore of aluminum forms as a result of weathering processes under tropical conditions. Its color varies from red or brown to nearly white. Figure 6.28 Bauxite. Did you know? Bauxite is a useful indicator of past climates because it records periods of wet tropical climate in the geologic past. Bauxite forms in rainy tropical climates. When aluminum-rich source rocks are subjected to the intense and prolonged chemical weathering of the tropics, most of the common elements, including calcium, sodium, and potassium, are removed by leaching. Because aluminum is extremely insoluble, it becomes concentrated in the soil. Thus, the formation of bauxite depends on climatic conditions in which chemical weathering and leaching are pronounced, plus, of course, the presence of aluminum-rich source rock. In a similar manner, important deposits of nickel and cobalt develop from igneous rocks rich in silicate minerals such as olivine. There is significant concern regarding the mining of bauxite and other residual deposits because they tend to occur in environmentally sensitive areas of the tropics. Mining is preceded by the removal of tropical vegetation, thus destroying rainforest ecosystems. Moreover, the thin moisture-retaining layer of organic matter is also disturbed. When the soil dries out in the hot sun, as has been mentioned, it becomes brick-like and loses its moisture-retaining qualities. Such soil cannot be productively farmed, nor can it support significant forest growth. The long-term consequences of bauxite mining are clearly of concern for developing countries in the tropics, where this important ore is mined. Other deposits. Many copper and silver deposits result when weathering processes concentrate metals that are dispersed through a low-grade primary ore. Usually such enrichment occurs in deposits containing pyrite, the most common and widespread sulfide mineral. Pyrite is important because when it chemically weathers, sulfuric acid forms, which enables percolating waters to dissolve the ore metals. Once dissolved, the metals gradually migrate downward through the primary ore body until they are precipitated. Deposition takes place because of changes that occur in the chemistry of the solution when it reaches the groundwater zone. In this manner, the small percentage of dispersed metal can be removed from a large volume of rock and redeposited as a higher grade or in a smaller volume of rock. Concept checks 6.8. 1. How can weathering create an ore deposit? 2. Name an important ore that is associated with weathering processes. Concepts in review: weathering and soils. 6.1 Weathering. Define weathering and distinguish between the two main categories of weathering. Key terms: weathering, mechanical weathering, chemical weathering. Weathering is the disintegration and decomposition of rocks on the surface of Earth. Rocks might break into many smaller pieces through physical processes called mechanical weathering. Rocks can also decompose as minerals react with environmental agents such as oxygen and water to produce new substances that are stable at Earth's surface. This is called chemical weathering. Would a shattered window be an example of mechanical weathering or chemical weathering? What about a rusty bicycle? 6.2 Mechanical weathering. List and describe 4 examples of mechanical weathering. Key terms: frost wedging, sheeting, exfoliation, dome joint. Mechanical weathering forces include the expansion of ice, the crystallization of salt, and the growth of plant roots. All work to pry apart grains and enlarge fractures. Rocks that form under lots of pressure deep in earth expand when they are exposed at the surface, and sometimes this expansion is great enough to cause the rock to break into onion-like layers. This sheeting can generate broad dome-shaped exposures of rock called exfoliation domes. This is a close-up view of a massive granite feature in the Sierra Nevada of California. Notice the thin slabs of granite that are separating from this rock mass. Describe the process that caused this to occur. What term describes the dome-like feature that results? 6.3 Chemical weathering. Discuss the importance of water and carbonic acid in chemical weathering processes. Key terms: oxidation, carbonic acid, spheroidal weathering. Water is by far the most important agent of chemical weathering. Oxygen dissolved in water oxidizes iron-rich minerals. Carbon dioxide dissolved in water forms carbonic acid, which attacks and alters rock. The chemical weathering of silicate minerals produces soluble products containing sodium, calcium, potassium, and magnesium ions, silica in solution, insoluble iron oxides such as hematite and limonite, and clay minerals. Spheroidal weathering results when sharp edges and corners of rocks are chemically weathered more rapidly than flat rock faces. The higher proportion of surface area for a given volume of rock at the edges and corners means there is more mineral material exposed to chemical attack. Faster weathering at the corners produces weathered rocks that become increasingly sphere-shaped over time. This sample of granite is rich in potassium, feldspar, and quartz. There are minor amounts of hornblende. If this rock were to undergo chemical weathering, how would its minerals change? List the products you would expect to result. Would all of the minerals decompose? If not, which mineral would likely remain relatively intact? 6.4 Rates of weathering. Summarize the factors that influence the type and rate of rock weathering. Key term: Differential weathering. Some types of rocks are more stable at Earth's surface than others, due to the minerals they contain. Different minerals break down at different rates under the same conditions. Quartz is the most stable silicate mineral, while minerals high in Bowen's reaction series such as olivine tend to decompose more rapidly. Rock weathers most rapidly in an environment with lots of heat to drive reactions in water to facilitate those reactions. Consequently, rocks decompose relatively quickly in hot, wet climates and slowly in cold, dry conditions. Frequently, rocks exposed at Earth's surface do not weather at the same rate. This differential weathering of rocks is influenced by factors such as mineral composition and degree of jointing. In addition, if a rock mass is protected from weathering by another, more resistant rock, then it will weather at a slower rate than a fully exposed equivalent rock. Differential weathering produces many of our most spectacular landforms. 6.5 Soil, an indispensable resource. Define soil and explain why soil is referred to as an interface. List and briefly discuss 5 controls of soil formation. Key terms. Regolith soil humus parent material. Soils are vital combinations of organic and inorganic components found at the interface where the geosphere, atmosphere, hydrosphere, and biosphere meet. This dynamic zone is the overlap between different parts of the Earth system. It includes the regolith's rocky debris mixed with humus, water, and air. Residual soils form in place due to the weathering of bedrock, whereas transported soils develop on unconsolidated sediment. Soils formed in different climates are different in part due to temperature and moisture differences but also due to the organisms that live in those different environments. These organisms can add organic matter or chemical compounds to the developing soil or can help mix the soil through their growth and movement. It takes time for soil to form. Soils that have developed for a longer period of time will have different characteristics than young soils. In addition, some minerals break down more readily than others. Soils produced from the weathering of different parent rocks are produced at different rates. The steepness of the slope on which a soil is forming is a key variable, with shallow slopes retaining their soils and steeper slopes shedding them to accumulate elsewhere. Label the 4 components of a soil on this pie chart. 6.6 Describing and classifying soils. Sketch, label, and describe an idealized soil profile. Explain the need for classifying soils. Key terms. Horizon soil profile, alluviation, leaching, solemn soil taxonomy. Despite the great diversity of soils around the world, there are some broad patterns to the vertical anatomy of soil layers. Organic material, called humus, is added at the top, mainly from plant sources. There, it mixes with mineral matter. At the bottom, bedrock breaks down and contributes mineral matter. In between, some materials are leached out or alluviated from higher levels and transported to lower levels, where they may form an impermeable layer called hardpan. The need to bring order to huge quantities of data motivated the establishment of a classification scheme for the world's soils. This soil taxonomy features 12 broad orders. Which soil order would likely contain a higher proportion of humus, inceptisol or histosol? Which soil order would be more likely found in Brazil, gelisol or oxisol? 6.7 The impact of human activities on soil. Explain the detrimental impact of human activities on soil. The clearing of tropical rainforests is an issue of concern. Most of the nutrients in the tropical rainforest ecosystem are not in the soil but in the trees. When the trees are removed from the rainforest, most of the nutrients are removed as well. The loss of vegetation also makes the soils highly susceptible to erosion. Once cleared of vegetation, soils may also be baked by the sun into a brick-like consistency. Soil erosion is a natural process, part of the constant recycling of earth materials that we call the rock cycle. Human activities have increased soil erosion rates over the past several hundred years. Because natural soil production rates are constant, there is a net loss of soil at a time when a record-breaking number of people live on the planet. Using windbreaks, terracing, installing grassed waterways, and plowing the land along horizontal contour lines are all practices that have been shown to reduce soil erosion. Why was this row of evergreens planted on an Indiana farm? 6.8 Weathering and/or deposits. Relate weathering to the formation of certain or deposits. Key term: secondary enrichment. Weathering creates or deposits by concentrating minor amounts of metals into economically valuable deposits. The process, often called secondary enrichment, is accomplished by either removing undesirable materials and leaving the desired elements enriched in the upper zones of the soil, or removing and carrying the desirable elements to lower soil zones, where they are redeposited and become more concentrated. Bauxite, the principal ore of aluminum, is one important ore created as a result of enrichment by weathering processes. In addition, many copper and silver deposits result when weathering processes concentrate metals that were formerly dispersed through low-grade primary ore. Give it some thought. 1. How are the two main categories of weathering represented in this image that shows human-made objects? 2. Describe how plants promote mechanical and chemical weathering but inhibit erosion. 3. Granite and basalt are exposed to Earth's surface in a hot, wet region. Will mechanical weathering or chemical weathering predominate? Which rock will weather more rapidly? Why? 4. The accompanying photo shows Shiprock, a well-known landmark in the northwestern corner of New Mexico. It is a massive igneous rock that represents the plumbing of a now-vanished volcanic feature. Extending toward the upper left is a related wall-like igneous structure known as a dike. The igneous features are surrounded by sedimentary rocks. Explain why these once deeply buried igneous features now stand high above the surrounding terrain. What term in section 6.4, Rates of Weathering, applies to this situation? 5. Due to burning of fossil fuels such as coal and petroleum, the level of carbon dioxide in the atmosphere has been increasing for more than 150 years. Should this increase tend to accelerate or slow down the rate of chemical weathering of Earth's surface rocks? Explain how you arrived at your conclusion. 6. In Chapter 4, you learned that feldspars are very common minerals in igneous rocks. When you learn about the common minerals that compose sedimentary rocks in Chapter 7, you will find that feldspars are relatively rare. Applying what you have learned about chemical weathering, explain why this is true. Based on this explanation, what mineral might you expect to be common in sedimentary rocks that is not found in igneous rocks? 7. The accompanying photo shows a footprint on the moon left by an Apollo astronaut in material popularly called lunar soil. Does this material satisfy the definition we use for soil on Earth? Explain why or why not. You may want to refer to Figure 6.14. 8. What might cause different soils to develop from the same kind of parent material or similar soils to form from different parent materials? 9. Using the map of global soil regions in Figure 6.19, identify the main soil order in the region adjacent to South America's Amazon River and the predominant soil order in the American Southwest. Briefly contrast these soils. Do they have anything in common? Referring to Table 6.2 might be helpful. 10. This soil sample is from a farm in the Midwest. From which horizon was the sample most likely taken, A, E, B, or C? Explain. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, and the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 7: Sedimentary Rocks. These eroded sedimentary layers are part of the Vermilion Cliffs, near Badger Creek in northern Arizona. Iron oxide colors some of the layers red. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 7.1 Explain the importance of sedimentary rocks and summarize the part of the rock cycle that pertains to sediments and sedimentary rocks. List the 3 categories of sedimentary rocks. 7.2 Describe the primary basis for distinguishing among detrital rocks and discuss how the origin and history of such rocks might be determined. 7.3 Explain the processes involved in the formation of chemical sedimentary rocks and list several examples. 7.4 Outline the successive stages in the formation of coal. 7.5 Describe the processes that convert sediment into sedimentary rock and other changes associated with burial. 7.6 Summarize the criteria used to classify sedimentary rocks. 7.7 Distinguish among 3 broad categories of sedimentary environments and provide an example of each. List several sedimentary structures and explain why these features are useful to geologists. 7.8 Distinguish between the 2 broad groups of non-metallic mineral resources. Discuss the 3 important fossil fuels associated with sedimentary rocks. 7.9 Relate weathering processes and sedimentary rocks to the carbon cycle. Chapter 6 provided the background you need to understand the origin of sedimentary rocks. Recall that weathering of existing rocks begins the process. Next, gravity and agents of erosion such as running water, wind, and glacial ice remove the products of weathering and carry them to a new location where they are deposited. Usually the particles are broken down further during this transport phase. Following deposition, this material, which is now called sediment, becomes lithified. It is from sedimentary rocks that geologists reconstruct many details of Earth's history. Because sediments are deposited in a variety of settings at the surface, the rock layers that they eventually form hold many clues about past surface environments. A layer may represent a desert sand dune, the muddy floor of a swamp, or a tropical coral reef. There are many possibilities. Many sedimentary rocks are associated with important energy and mineral resources and are therefore important economically as well. 7.1 An Introduction to Sedimentary Rocks. Explain the importance of sedimentary rocks and summarize the part of the rock cycle that pertains to sediments and sedimentary rocks. List the 3 categories of sedimentary rocks. Most of the solid Earth consists of igneous and metamorphic rocks. Geologists estimate that these 2 categories represent 90 to 95% of the outer 16 kilometers of the crust. Nevertheless, most of Earth's solid surface consists of either sediment or sedimentary rock. Importance. About 75% of land areas are covered by sediments and sedimentary rocks. Across the ocean floor, which represents about 70% of Earth's solid surface, virtually everything is covered by sediment. Igneous rocks are exposed only at the crests of mid-ocean ridges and in some volcanic areas. Thus, while sediment and sedimentary rocks make up only a small percentage of Earth's crust, they are concentrated at or near the surface, the interface among the geosphere, hydrosphere, atmosphere, and biosphere. Because of this unique position, sediments and the rock layers that they eventually form contain evidence of past conditions and events at the surface. Based on the compositions, textures, structures, and fossils in sedimentary rocks, experienced geologists can decipher clues that provide insights into past climates, ecosystems, and ocean environments. Furthermore, by studying sedimentary rocks, geologists can reconstruct the configuration of ancient land masses and the locations and compositions of long-vanished mountain systems. In short, this group of rocks provides geologists with much of the basic information needed to reconstruct the details of Earth history. Because they contain fossils and other clues about the geologic past, sedimentary rocks are important in the study of Earth history. Vertical changes in rock types represent environmental changes through time. These strata are exposed at Karijini National Park, Western Australia. Figure 7.1 Sedimentary Rocks Record Change. The study of sedimentary rocks has economic significance as well. Coal, which provides a significant portion of our electrical energy, is classified as a sedimentary rock. Moreover, other major energy sources, including oil, natural gas, and uranium, are derived from sedimentary rocks. So are major sources of iron, aluminum, manganese, and phosphate fertilizer, plus numerous materials that are essential to the construction industry, such as cement and aggregate. Sediments and sedimentary rocks are also the primary reservoir of groundwater. Thus, an understanding of this group of rocks and the processes that form and modify them is basic to locating and maintaining supplies of many important resources. Origins. Like other rocks, the sedimentary rocks that we see around us and use in so many different ways have their origin in the rock cycle. Figure 7.2 illustrates the portion of the rock cycle that occurs near Earth's surface, the part that pertains to sediments and sedimentary rocks. A brief overview of these processes provides a useful perspective. Beginning with weathering, this diagram outlines the portion of the rock cycle that pertains to the formation of sedimentary rocks. Smart Figure 7.2 The Big Picture. Smart Figure 7.2 Full Alternative Text Description Watch Tutorial, Depositional Environments. Weathering begins the process. It involves the physical disintegration and chemical decomposition of pre-existing igneous, metamorphic, and sedimentary rocks. Weathering generates a variety of products subject to erosion, including various solid particles and ions in solution. These are the raw materials for sedimentary rocks. Soluble constituents are dissolved and carried away by runoff and groundwater. Solid particles are frequently moved downslope by gravity, a process termed mass wasting, before running water, groundwater, wave activity, wind, and glacial ice remove them. These agents of transport, covered in detail in later chapters, move these materials from the sites where they originated to locations where they accumulate. The transport of sediment is usually intermittent. For example, during a flood, a rapidly moving river moves large quantities of sand and gravel. As the floodwaters recede, particles are temporarily deposited, only to be moved again by a subsequent flood. Deposition of solid particles occurs when wind and water currents slow down and as glacial ice melts. The word sedimentary actually refers to this process. It is derived from the Latin sedimentum, which means to settle, a reference to solid material settling out of a fluid. The mud on the floor of a lake, a delta at the mouth of a river, a gravel bar in a streambed, the particles in a desert sand dune, and even household dust are examples. The deposition of material dissolved in water is not related to the strength of water currents. Rather, ions in solution are removed when chemical or temperature changes cause material to crystallize and precipitate, or when organisms remove dissolved material to build hard parts such as shells. As deposition continues, older sediments are buried beneath younger layers and gradually converted to sedimentary rock by compaction and cementation. This and other changes are referred to as diagenesis, a collective term for all the changes that take place in texture, composition, and other physical properties after sediments are deposited. Because the products of weathering are transported, deposited, and transformed into solid rock in a variety of ways, geologists recognize three categories of sedimentary rocks. As this overview reminds us, sediment has two principal sources. First, it may be an accumulation of material that originates and is transported as solid particles derived from both mechanical and chemical weathering. Deposits of this type are termed detrital, and the sedimentary rocks they form are called detrital sedimentary rocks. The second major source of sediment is soluble material produced largely by chemical weathering. When these ions in solution are precipitated by either inorganic or biological processes, the material is known as chemical sediment, and the rocks formed from it are called chemical sedimentary rocks. The third category is organic sedimentary rocks. These rocks form from the carbon-rich remains of organisms. The primary example is coal. This black combustible rock consists of organic carbon from the remains of plants that died and accumulated on the floor of a swamp. The bits and pieces of undecayed plant material that constitute the sediments in coal are quite unlike the weathering products that make up detrital and chemical sedimentary rocks. Concept checks 7.1. 1. How does the volume of sedimentary rocks in Earth's crust compare to the volume of igneous and metamorphic rocks? 2. List two ways in which sedimentary rocks are important. 3. Outline the steps that would transform an exposure of granite in the mountains into various sedimentary rocks. 4. List and briefly describe the differences among the three basic sedimentary rock categories. 7.2 Detrital sedimentary rocks. Describe the primary basis for distinguishing among detrital rocks and discuss how the origin and history of such rocks might be determined. Though a wide variety of minerals and rock fragments may be found in detrital rocks, clay minerals and quartz are the chief constituents of most sedimentary rocks in this category. Recall from Chapter 6 that clay minerals are the most abundant product of the chemical weathering of silicate minerals, especially the feldspars. Clays are fine-grained minerals with sheet-like crystalline structures similar to the micas. The other common mineral, quartz, is abundant because it is extremely durable and very resistant to chemical weathering. Thus, when igneous rocks such as granite are attacked by weathering processes, individual quartz grains are freed. Other common minerals in detrital rocks are feldspars and micas. Because chemical weathering rapidly transforms these minerals into new substances, their presence in sedimentary rocks indicates that erosion and deposition occurred fast enough to preserve some of the primary minerals from the source rock before they could be decomposed. Particle size is the primary basis for distinguishing among various detrital sedimentary rocks. Figure 7.3 presents the size categories for particles making up detrital rocks. Particle size allows us to distinguish detrital rocks, and the sizes of the component grains also provide useful information about environments of deposition. Currents of water or air sort the particles by size. The stronger the current, the larger the particle size that can be carried. Gravels, for example, are moved by swiftly flowing rivers as well as by landslides and glaciers. Less energy is required to transport sand, thus, sand is found in such features as wind-blown dunes and some river deposits and beaches. Very little energy is needed to transport clay, so it settles very slowly. Accumulation of these tiny particles is generally associated with the quiet water of a lake, lagoon, swamp, or certain marine environments. Particle size is the primary basis for distinguishing among various detrital sedimentary rocks. Figure 7.3 Particle size categories. Figure 7.3 Full alternative text description. In order of increasing particle size, common detrital sedimentary rocks include shale, sandstone, and conglomerate or breccia. We will now look at each type and how it forms. Shale. Shale is a sedimentary rock consisting of silt and clay-sized particles. These fine-grained detrital rocks account for well over half of all sedimentary rocks. The particles in these rocks are so small that they cannot be readily identified without great magnification, and this makes shale more difficult to study and analyze than most other sedimentary rocks. Dark shale containing fossilized plant remains is relatively common. How does shale form? Figure 7.4 Shale, the most abundant sedimentary rock. Much of what can be learned about the process that forms shale is related to particle size. The tiny grains in shale indicate that deposition occurs as a result of gradual settling from relatively quiet, non-turbulent currents. Such environments include lakes, river floodplains, lagoons, and portions of the deep ocean basins. Even in these quiet environments, there is usually enough turbulence to keep clay-sized particles suspended almost indefinitely. Consequently, much of the clay is deposited only after the individual particles coalesce to form larger aggregates. Sometimes the chemical composition of rock provides additional information. One example is black shale, which is black because it contains abundant organic matter. When such a rock is found, it strongly implies that deposition occurred in an oxygen-poor environment such as a swamp, where organic materials do not readily oxidize and decay. Did you know? The term clay may be confusing because it has more than one meaning. In the context of detrital particle size, the term clay refers to grains less than 1/256 mm, which are thus microscopic. However, the term clay is also used as the name of a group of silicate minerals. Although most clay minerals are of clay size, not all clay-sized sediment consists of clay minerals. Thin layers. As silt and clay accumulate, they tend to form thin layers, which are commonly referred to as laminae. Initially, the particles in the laminae are oriented randomly. This disordered arrangement leaves a high percentage of open space that is filled with water. However, this situation usually changes over time as additional layers of sediment pile up and compact the sediment below. During this phase, the clay and silt particles take on a more nearly parallel alignment and become tightly packed. This rearrangement of grains reduces the size of the pore spaces and forces out much of the water. Once the grains are pressed closely together, the tiny spaces between particles do not readily permit solutions containing cementing material to circulate. Therefore, geologists often describe shales as being weak because they are poorly cemented and therefore not well lithified. The inability of water to penetrate shales' microscopic pore spaces explains why this rock often forms barriers to the subsurface movement of water and petroleum. Indeed, rock layers that contain groundwater are commonly underlain by shale beds that block further downward movement. The opposite is true for underground reservoirs of petroleum. They are often capped by shale beds that effectively prevent oil and gas from escaping to the surface. The relationship between impermeable beds and the occurrence and movement of groundwater is examined in Chapter 14. Shale beds can be cap rocks in oil traps and are discussed later in the chapter. Did you know? The Navajo sandstone pictured in Figure 7.8 represents a vast area of sand dunes that once covered up to 400,000 square kilometers, an area the size of California. Shale, mudstone, or siltstone. It is common to apply the term shale to all fine-grained sedimentary rocks, especially in a non-technical context. However, be aware that there is a more restricted use of the term. In this narrower usage, shale must exhibit the ability to split into thin layers along well-developed, closely spaced planes. This property is termed fissility. Fissilis equals that which can be cleft or split. If the rock breaks into chunks or blocks, the name mudstone is applied. Another fine-grained sedimentary rock that, like mudstone, is often grouped with shale but lacks facility is siltstone. As its name implies, siltstone is composed largely of silt-sized particles and contains less clay-sized material than shale and mudstone. Gentle slopes. Although shale is far more common than other sedimentary rocks, it does not usually attract as much notice as other, less abundant, members of this group. The reason is that shale does not form prominent outcrops, as sandstone and limestone often do. Rather, shale crumbles easily and usually forms a cover of soil that hides the unweathered rock below. This is illustrated nicely in the Grand Canyon, where the gentler slopes of weathered shale are quite inconspicuous and overgrown with vegetation, in sharp contrast with the bold cliffs produced by more durable rocks. Beds of resistant sandstone and limestone produce bold cliffs. Weaker, poorly cemented shale produces gentler slopes of weathered debris. Figure 7.5 Shale crumbles easily. Although shale beds may not form striking cliffs and prominent outcrops, some deposits have economic value. Certain shales are quarried to obtain raw material for pottery, brick, tile, and china. Moreover, when mixed with limestone, shale is used to make Portland cement. Some shales contain substantial quantities of oil and natural gas that can be obtained by a process called hydraulic fracturing. There is more about this process in the section on energy resources later in the chapter. Sandstone. Sandstone is the name given to rocks in which sand-sized grains predominate. After shale, sandstone is the next most abundant sedimentary rock, accounting for approximately 20% of the entire group. Sandstones form in a variety of environments, and clues such as the composition, shape, and sorting of the grains may provide information about the environment in which the sediment was deposited. After shale, sandstone is the next most abundant sedimentary rock. Figure 7.6 Quartz sandstone. Sorting. All the particles in sandstone are not necessarily identical in size. Sorting refers to the degree of similarity in particle size in a sedimentary rock. For example, if all the grains in a sample of sandstone are about the same size, the sand is considered well sorted. Conversely, if the rock contains mixed large and small particles, the sand is said to be poorly sorted. By studying the degree of sorting, we can learn much about the depositing current. Deposits of wind-blown sand are usually better sorted than deposits sorted by wave activity. Particles washed by waves are commonly better sorted than materials deposited by streams. Sediment accumulations that exhibit poor sorting usually result when particles are transported for only a relatively short time and then rapidly deposited. For example, when a turbulent stream reaches the gentler slopes at the base of a steep mountain, its velocity is quickly reduced, and poorly sorted sands and gravels are deposited. Sorting refers to the range of particle sizes present in a rock. Geologists describe a particle's shape in terms of its angularity and sphericity. Smart Figure 7.7 Full alternative text description. Smart Figure 7.7 Sorting and particle shape. Watch tutorial, Sorting and Rounding. The Navajo sandstone represents a vast area of ancient sand dunes that once covered an area the size of California. These modern dunes are among the highest in North America. Figure 7.8 Full alternative text description. Particle shape. Figure 7.8 Sand dunes consist of well-sorted sediment. The shapes of sand grains can also help decipher the history of a sandstone. When streams, winds, or waves move sand and other larger sedimentary particles, the grains lose their sharp edges and corners and become more rounded as they collide with other particles during transport. Thus, rounded grains likely have been airborne or waterborne. Further, the degree of rounding indicates the distance or time involved in the transportation of sediment by currents of air or water. Highly rounded grains indicate that a great deal of abrasion and hence a great deal of transport has occurred. Very angular grains, on the other hand, can imply either of two things: that the materials were transported only a short distance before they were deposited, or that they were carried by some medium other than water or wind. For example, when glaciers move sediment, the particles are usually made more irregular by the crushing and grinding action of the ice. Transport affects mineral composition. In addition to affecting the degree of rounding and the amount of sorting that particles undergo, the length of transport by turbulent air and water currents also influences the mineral composition of a sedimentary deposit. Substantial weathering and long transport lead to the gradual destruction of weaker and less stable minerals, including the feldspars and ferromagnesians. Because quartz is very durable, it is the mineral that best survives a long trip in a turbulent environment. To summarize, the origin and history of sandstone can often be deduced by examining the sorting, roundness, and mineral composition of its constituent grains. Knowing this information allows us to infer that a well-sorted, quartz-rich sandstone consisting of highly rounded grains must be the result of a great deal of transport. Such a rock, in fact, may represent several cycles of weathering, transport, and deposition. We may also conclude that a sandstone containing significant amounts of feldspar and angular grains of ferromagnesian minerals underwent little chemical weathering and transport and was probably deposited close to the source area of the rock particles. Varieties of sandstone. Due to its durability, quartz is the predominant mineral in most sandstones. Such rock is often simply called quartz sandstone. When a sandstone contains appreciable quantities of feldspar, the rock is called arkose. In addition to feldspar, arkose usually contains quartz and sparkling bits of mica. The mineral composition of arkose indicates that the grains were derived from granitic source rocks. The particles are generally poorly sorted and angular, which suggests short-distance transport, minimal chemical weathering in a relatively dry climate, and rapid deposition and burial. Did you know? The most important and common material used for making glass is silica, which is usually obtained from the quartz in clean, well-sorted sandstones. A third variety of sandstone is known as greywack. Along with quartz and feldspar, this dark-colored rock contains abundant rock fragments and matrix, finer-grained material in which the fragments are embedded. More than 15% of greywack's volume is matrix. The poor sorting and angular grains characteristic of greywack suggest that the particles were transported only a relatively short distance from their source area and were then rapidly deposited. Before the sediment could be reworked and sorted further, it was buried by additional layers of material. Greywack is frequently associated with submarine deposits made by dense sediment-choked torrents called turbidity currents. Conglomerate and breccia. Conglomerate consists largely of gravels. As Figure 7.3 indicates, these particles can range in size from large boulders to particles as small as peas. The particles are often large enough to be identified as distinctive rock types, thus, they can be valuable in identifying the source areas of sediments. More often than not, conglomerates are poorly sorted, and the spaces between the large gravel particles contain sand or mud. The gravel-sized particles in this rock are rounded. Gravel deposits along Carbon Creek in Grand Canyon National Park are poorly sorted. Figure 7.9 Conglomerate. Figure 7.10 Poorly sorted sediments. Gravels accumulate in a variety of environments and usually indicate the existence of steep slopes or very turbulent currents. The coarse particles in a conglomerate may reflect the action of energetic mountain streams or result from strong wave activity along a rapidly eroding coast. Some glacial and landslide deposits also contain plentiful gravel. If the large particles are angular rather than rounded, the rock is called breccia. Because large particles abrade and become rounded very rapidly during transport, the pebbles and cobbles in a breccia indicate that they did not travel far from their source area before they were deposited. Thus, as with many other sedimentary rocks, conglomerates and breccias contain clues to their history. Their particle sizes reveal the strength of the currents that transported them, and the degree of rounding indicates how far the particles traveled. The fragments within a sample identify the source rocks that supplied them. Concept checks 7.2. 1. What minerals are most abundant in detrital sedimentary rocks? In which rocks do these minerals predominate? 2. What is the primary basis for distinguishing among detrital rocks? 3. Describe how sediments become sorted. What would cause sediments to be poorly sorted? 4. Distinguish between conglomerate and breccia. 7.3 Chemical sedimentary rocks. Explain the processes involved in the formation of chemical sedimentary rocks and list several examples. In contrast to detrital rocks, which form from the solid products of weathering, chemical sediments derive from ions that are carried in solution to lakes and seas. This material does not remain dissolved in the water indefinitely, however. Some of it precipitates to form chemical sediments. These become rocks such as limestone, chert, and rock salt. This precipitation of material occurs in two ways. Inorganic processes such as evaporation and chemical activity can produce chemical sediments. Organic processes of water-dwelling organisms also form chemical sediments, said to be of biochemical origin. One example of a deposit resulting from inorganic chemical processes is the dripstone that decorates many caves. Another is the salt left behind as a body of seawater evaporates. In contrast, many water-dwelling animals and plants extract dissolved mineral matter to form shells and other hard parts. After the organisms die, their skeletons collect by the millions on the floor of a lake or an ocean as biochemical sediment. An example of a chemical sedimentary rock with an inorganic origin. Figure 7.11 Cave deposits. This variety of limestone consists of shell fragments, therefore, it has a biochemical origin. Rock sample photo by E. J. Tarbuck. Beach photo by Donald R. Fraser Photo Library Incorporated Alamy. Images. Limestone. Figure 7.12 Coquina. Representing about 10% of the total volume of all sedimentary rocks, limestone is the most abundant chemical sedimentary rock. It is composed chiefly of the mineral calcite and forms either by inorganic means or as a result of biochemical processes. Although the mineral composition of all limestone is similar, many different types exist, reflecting the varied conditions under which limestone originates. Forms that have a marine biochemical origin are by far the most common. Carbonate reefs. Corals are one important example of organisms that are capable of creating large quantities of marine limestone. These relatively simple invertebrate animals secrete a calcareous external skeleton. Although they are small, corals are capable of creating massive structures called reefs. Reefs consist of coral colonies made up of great numbers of individuals that live side by side on a calcite structure secreted by the animals. In addition, calcium carbonate, secreting algae live with the corals and help cement the entire structure into a solid mass. A wide variety of other organisms also live in and near the reefs. Large quantities of biochemical limestone are created by reef-building organisms. Figure 7.13 Carbonate reefs. Figure 7.13 Full alternative text description. Certainly the best-known modern reef is Australia's 2,600-kilometer-long Great Barrier Reef, but many lesser reefs also exist. They develop in the shallow, warm waters of the tropics and subtropics. Equatorward of about 30 degrees latitude. Striking examples exist in the Bahamas, Hawaii, and the Florida Keys. Modern corals were not the first reef builders. Earth's first reef-building organisms were photosynthesizing bacteria that lived during Precambrian time, more than 2 billion years ago. From fossil remains, it is known that a variety of organisms have constructed reefs, including bivalves, bryozoans, and sponges. Corals have been found in fossil reefs as ancient as 500 million years old, but corals similar to the modern colonial varieties have constructed reefs only during the past 60 million years. In the United States, reefs of Silurian age are prominent features in Wisconsin, Illinois, and Indiana. In western Texas and adjacent southeastern New Mexico, a massive reef complex that formed during the Permian period is strikingly exposed in Guadalupe Mountains National Park. Coquina and chalk. Although a great deal of limestone is produced by biological processes, this origin is not always evident because shells and skeletons may undergo considerable change before becoming lithified into rock. However, one easily identified biochemical limestone is coquina, a coarse rock composed of poorly cemented shells and shell fragments. Another less obvious but nevertheless familiar example is chalk, a soft, porous rock made up almost entirely of the hard parts of microscopic marine organisms. Among the most famous chalk deposits are those exposed along the southeast coast of England. This prominent deposit underlies large portions of southern England as well as parts of northern France. Figure 7.14 The White Chalk Cliffs. Figure 7.14 Full alternative text description. Inorganic limestones. Limestones having an inorganic origin form when chemical changes or high water temperatures cause calcium carbonate to precipitate out of the water. Travertine, the type of limestone commonly seen in caves, is an example. When travertine is deposited in caves, groundwater is the source of the calcium carbonate. As water droplets become exposed to the air in a cavern, some of the carbon dioxide dissolved in the water escapes, causing calcium carbonate to precipitate. Another variety of inorganic limestone is oolitic limestone, a rock composed of small spherical grains called ooids. Ooids form in very shallow marine waters as tiny seed particles are moved back and forth with currents. As the grains are rolled about in the warm water, which is supersaturated with calcium carbonate, they become coated with layer upon layer of the chemical precipitate. Oolitic limestone is an inorganic limestone composed of ooids. Note the dime coin for scale. Figure 7.15 Full alternative text description. Figure 7.15 Oolitic limestone. Dolostone. Closely related to limestone is dolostone, a rock composed of the calcium-magnesium carbonate mineral dolomite. Although dolostone and limestone sometimes closely resemble one another, they can be easily distinguished by observing their reaction to dilute hydrochloric acid. When a drop of acid is placed on limestone, the reaction is obvious. However, unless dolostone is powdered, it does not visibly react to the acid. Dolostone's origins remain a subject of discussion among geologists. No marine organisms produce hard parts of dolomite, and the chemical precipitation of dolomite from seawater occurs only under conditions of unusual water chemistry in certain nearshore sites. Yet dolostone is abundant in many ancient sedimentary rock successions. It appears that a significant proportion of dolostone is produced when magnesium-rich waters circulate through limestone and replace some calcium ions with magnesium ions. However, not all dolostones appear to be formed by such a process, and their origin remains uncertain. Chert. Chert is a name used for a number of very compact and hard rocks made of microcrystalline quartz. It can vary in color from nearly white to black. Chert often appears gray, brown, or brownish-gray and can even appear red or greenish. Color variations are related to trace elements present in the rock. Figure 7.16 shows some varieties. One well-known form is flint, whose dark color results from the organic matter it contains. Jasper, a red variety, gets its bright color from iron oxide. Petrified wood is chert that is made when silica-rich material such as volcanic ash buries trees. As groundwater-rich and dissolved silica from the ash penetrates the wood, silica precipitates, gradually replacing the wood. Fine structures such as growth rings are often preserved. Like glass, most chert has a conchoidal fracture. Its hardness, ease of chipping, and ability to hold a sharp edge made chert a favorite of Native Americans for fashioning points for spears and arrows. Because of chert's durability and extensive use, arrowheads are found in many parts of North America. Chert is the name applied to a number of dense, hard chemical sedimentary rocks made of microcrystalline quartz. Petrified wood photo by Gracious Tiger Shutterstock, flint and jasper photos by E. J. Tarbuck. Arrowhead photo by Daniel Sombrow's Science Source. Figure 7.16 Colorful chert. Figure 7.16 Full alternative text description. Did you know? In the western and southwestern United States, sedimentary rocks often exhibit a brilliant array of colors. The walls of Arizona's Grand Canyon feature layers that are red, orange, purple, gray, brown, and buff. Some of the sedimentary rocks in Utah's Bryce Canyon are a delicate pink color. Sedimentary rocks in more humid places are also colorful, but they are usually covered by soil and vegetation. The most important pigments are iron oxides, and only very small amounts are needed to color a rock. Hematite tints rocks red or pink, whereas limonite produces shades of yellow and brown. When sedimentary rocks contain organic matter, it often colors the rocks black or gray. Chert most commonly occurs either as layered deposits, called bedded cherts, or as somewhat spherical masses called nodules, which form within other rocks and range in diameter from pea-size to several centimeters. Most bedded cherts are believed to originate from tiny marine organisms that produce hard parts from silica rather than calcium carbonate. These organisms extract silica from seawater. When they die, their hard parts may accumulate on the seafloor. Some bedded cherts occur in association with lava flows and layers of volcanic ash. For these occurrences, it is probable that the silica was derived from the decomposition of the volcanic ash and not from biochemical sources. Chert nodules are sometimes referred to as secondary cherts or replacement cherts. They form when silica, originally deposited in one place, dissolves, migrates, and then chemically precipitates elsewhere, replacing older material. Evaporites. In the geologic past, many areas that are now dry land were shallow marine bays with only a narrow connection to the open ocean. Under these conditions, seawater continually moved into the bay to replace water lost by evaporation. Eventually, the waters of the bay became saturated, and salt deposition began. Such deposits are called evaporites. Did you know? Each year about 30% of the world's supply of salt is extracted from seawater. The seawater is pumped into ponds and allowed to evaporate, leaving behind artificial evaporites, which are harvested. Minerals commonly precipitated in this fashion include halite, which is the chief component of rock salt, and gypsum, which is the main ingredient in rock gypsum. Both have economic importance. In addition to its familiar role as table salt, halite has many other uses, from melting ice on roads to making hydrochloric acid. People have sought, traded, and fought over it for much of human history. Gypsum is the basic ingredient in plaster of Paris and is used in making wallboard and interior plaster. When a body of seawater evaporates, the minerals that precipitate do so in a sequence that is determined by their solubility. Less soluble minerals precipitate first, and more soluble minerals precipitate later, as salinity increases. For example, gypsum precipitates when about 80% of the seawater has evaporated, and halite crystallizes when 90% of the water has been removed. During the last stages of this process, potassium and magnesium salts precipitate. One of these last-formed salts, the mineral sylvite, is mined as a significant source of potassium for fertilizer. On a smaller scale, evaporite deposits can be seen in such places as Death Valley, California. Here, following rains or periods of snowmelt in the mountains, streams flow from the surrounding mountains into an enclosed basin. As the water evaporates, dissolved minerals precipitate on the surface, forming a salt flat. Utah's extensive Bonneville Salt Flats, pictured in Figure 7.17, are another well-known example. This well-known Utah site was once a large salt lake. Smart Figure 7.17 Bonneville Salt Flats. Watch tutorial, Bonneville Salt Flats. Concept checks 7.3. 1. Explain how the formation of biochemical sediments differs from the formation of sediments formed by inorganic processes. Use examples as part of your explanation. 2. Distinguish among limestone, dolostone, and chert. Describe several varieties of each. 3. How do evaporites form? What are some examples? 7.4 Coal, an organic sedimentary rock. Outline the successive stages in the formation of coal. Coal is different from other sedimentary rocks. Unlike limestone and chert, which are rich in calcite and silica, coal is made of organic matter. Close examination of coal under a magnifying glass often reveals plant structures such as leaves, bark, and wood that have been chemically altered but are still identifiable. This supports the conclusion that coal is the end product of large amounts of plant material being buried for millions of years. The formation of coal involves these stages. Successive stages in the formation of coal. Smart Figure 7.18 From plants to coal. Smart Figure 7.18 Full alternative text description. Watch tutorial, coal. 1. Accumulation of plant remains. The initial stage in coal formation is the accumulation of large quantities of plant remains. Such accumulations result from special conditions because dead plants readily decompose when exposed to the atmosphere or other oxygen-rich environments. One important environment that allows for the buildup of plant material is a swamp. Stagnant swamp water is oxygen deficient, so complete decay of the plant material is not possible. Instead, the plants are attacked by certain bacteria that partly decompose the organic material and liberate oxygen and hydrogen. As these elements escape, the percentage of carbon in the plant matter gradually increases. The bacteria are not able to finish the job of decomposition because their growth is impeded by acids liberated from the plants. 2. Formation of peat. The partial decomposition of plant remains in an oxygen-poor swamp creates a layer of peat, a soft brown material in which plant structures are still easily recognized. With shallow burial, peat slowly changes to lignite, a soft brown coal. Burial increases the temperature of sediments as well as the pressure on them. 3. Formation of lignite and bituminous coal. Higher temperatures bring about chemical reactions within the plant materials and yield water and organic gases. As the load increases from more sediment on top of the developing coal, the water and volatiles are pressed out, and the proportion of fixed carbon increases. The greater the carbon content, the greater the coal's energy ranking as a fuel. During burial, the coal also becomes increasingly compact. For example, deeper burial transforms lignite into a harder, more compacted black rock called bituminous coal. A bed of bituminous coal may be only 1/10 as thick as the peat bed from which it formed. 4. Formation of anthracite coal. Lignite and bituminous coals are sedimentary rocks. However, when sedimentary layers are subjected to the folding and deformation associated with mountain building, the heat and pressure cause a further loss of volatiles and water, thus increasing the concentration of fixed carbon. This metamorphoses bituminous coal into anthracite, a very hard, shiny, black metamorphic rock. Although anthracite is a clean-burning fuel, only a relatively small amount of it is mined. Anthracite is not widespread and is more difficult and expensive to extract than the relatively flat-lying layers of bituminous coal. Coal is a major energy resource. Its role as a fuel and some of the problems associated with burning coal are discussed later in the chapter. Concept checks 7.4. 1. What is the raw material for coal? Under what circumstances does it accumulate? 2. Outline the successive stages in the formation of coal. 7.5. Turning sediment into sedimentary rock, diagenesis and lithification. Describe the processes that convert sediment into sedimentary rock and other changes associated with burial. We've seen that sediments change as they are converted to sedimentary rock. The term diagenesis is a collective term for all the chemical, physical, and biological changes that take place after sediments are deposited and during and after lithification to form sedimentary rock. Diagenesis is distinct from the metamorphic processes that may later convert a sedimentary rock to a metamorphic one. Did you know? In 2015, about 40% of the electricity generated in the United States was generated from coal. Diagenesis. Burial promotes diagenesis because as sediments are buried, they are subjected to increasing temperatures and pressures. Diagenesis occurs within the upper few kilometers of Earth's crust, at temperatures that are generally less than 150 to 200 C. Beyond this somewhat arbitrary temperature threshold, metamorphism is said to occur. One example of diagenetic change is recrystallization, the development of more stable minerals from less stable ones. For example, the mineral aragonite is the less stable form of calcium carbonate. Aragonite is secreted by many marine organisms to form shells and other hard parts, such as the skeletal structures produced by corals. In some environments, large quantities of these solid materials accumulate as sediment. As burial takes place, aragonite recrystallizes to the more stable form of calcium carbonate, calcite, the main constituent in the sedimentary rock limestone. Another example of diagenesis is the chemical alterations that take place as plant matter is buried gradually in an oxygen-poor environment, evolving into peat and then into coal. Lithification. Diagenesis includes lithification, the processes by which unconsolidated sediments are transformed into solid sedimentary rocks. Basic lithification processes include compaction and cementation. Figure 7.19 Compaction and cementation. Figure 7.19 Full alternative text description. Compaction. The most common physical diagenetic change is compaction. As described earlier, as sediment accumulates, the weight of overlying material compresses the deeper sediments. The deeper a sediment is buried, the more it is compacted and the firmer it becomes. As the grains are pressed closer and closer, there is considerable reduction in pore space. For example, when clays are buried beneath several thousand meters of material, the volume of the clay layer may be reduced by as much as 40%. As pore space decreases, much of the water that was trapped in the sediments is driven out. Because sands and other coarse sediments are less compressible, compaction is most significant as a lithification process in fine-grained sedimentary rocks such as shale. Cementation. The most important process by which sediments are converted to sedimentary rock is cementation, a process in which ions carried in solution by groundwater crystallize in the spaces between sediment grains to form minerals that gradually cement the grains together. Like compaction, this process reduces a rock's porosity. Calcite, silica, and iron oxide are the most common cements. It is often a relatively simple matter to identify the cementing material. Calcite cement will effervesce in contact with dilute hydrochloric acid. Silica is the hardest cement and thus produces the hardest sedimentary rocks. An orange or dark red color in a sedimentary rock means that iron oxide is present. While compaction and cementation are the main lithification processes for most types of sediment, in some cases the original sedimentary particles themselves undergo dissolution and recrystallization. For example, with time and burial, loose sediment consisting of delicate calcium carbonate, rich skeletal debris may be recrystallized into a relatively dense crystalline limestone. Because crystals grow until they fill all the available space, crystalline sedimentary rocks often lack pore spaces. Unless the rocks later develop joints and fractures, they will be relatively impermeable to fluids such as water and oil. Evaporites form initially as solid masses of intergrown crystals and hence can be similarly impermeable. Concept checks 7.5. 1. What is diagenesis? 2. Compaction is most important as a lithification process with which sediment size? 3. List 3 common cements. How might each be identified? 7.6 Classification of sedimentary rocks. Summarize the criteria used to classify sedimentary rocks. The classification chart in Figure 7.20 divides sedimentary rocks into major groups, detrital on the left side and chemical organic on the right. Further, you can see that the main criterion for subdividing the detrital rocks is particle size, whereas the primary basis for distinguishing among different rocks in the chemical group is their mineral composition. The main criterion for naming detrital rocks is particle size. The primary basis for naming chemical and organic sedimentary rocks is their composition. Figure 7.20 Identification of sedimentary rocks. Figure 7.20 Full alternative text description. As is the case with many classifications of natural phenomena, the categories presented in Figure 7.20 are more rigid than the actual state of nature. In reality, many of the sedimentary rocks classified into the chemical group also contain at least small quantities of detrital sediment. Many limestones, for example, contain varying amounts of mud or sand, giving them a sandy or shaly quality. Conversely, because practically all detrital rocks are cemented with material that was originally dissolved in water, they too are far from being pure. As was the case with the igneous rocks examined in Chapter 5, texture is a part of sedimentary rock classification. There are 2 major textures used in the classification of sedimentary rocks: clastic and non-clastic. The term clastic is taken from a Greek word meaning broken. Rocks that display a clastic texture consist of discrete fragments and particles that are cemented and compacted together. Although cement is present in the spaces between particles, these openings are rarely filled completely. All detrital rocks have a clastic texture. In addition, some chemical sedimentary rocks exhibit this texture. For example, coquina, the limestone composed of shells and shell fragments, is obviously as clastic as a conglomerate or sandstone. The same applies to some varieties of oolitic limestone. Some chemical sedimentary rocks have a non-clastic, or crystalline texture, in which the minerals form a pattern of interlocking crystals. The crystals may be microscopically small or large enough to be visible without magnification. Evaporites are of this type. As described earlier, some limestones originate as clastic deposits of shell fragments and subsequently undergo recrystallization. Chert can have a similar history. Like other evaporites, rock salt has a non-clastic texture because it is composed of intergrown crystals. Figure 7.21 Rock salt. Because they consist of intergrown crystals, non-clastic sedimentary rocks may resemble igneous rocks. The 2 rock types are usually easy to distinguish because the minerals contained in non-clastic sedimentary rocks are quite unlike those found in most igneous rocks. Concept checks 7.6. 1. What is the primary basis for distinguishing different chemical sedimentary rocks? How is the naming of detrital rocks different? 2. Distinguish between clastic and non-clastic textures. Which texture is associated with all detrital rocks? 7.7 Sedimentary rocks represent past environments. Distinguish among three broad categories of sedimentary environments and provide an example of each. List several sedimentary structures and explain why these features are useful to geologists. Sedimentary rocks are important to interpreting Earth's history. By understanding the conditions under which sedimentary rocks form, geologists can often deduce the history of a rock, including information about the origin of its component particles, the method of sediment transport, and the nature of the place where the grains eventually came to rest, that is, the environment of deposition. Smart Figure 7.22 Utah's Capitol Reef National Park. These tilted sedimentary strata are part of the water pocket fold at Halls Creek. The strata here record changing environments during the Mesozoic era. Importance of sedimentary environments. Watchmobile field trip, the sedimentary rocks of Capitol Reef National Park. An environment of deposition, or sedimentary environment, is a geographic setting where sediment is accumulating. Each site is characterized by a particular combination of geologic processes and environmental conditions. Some sediments, such as the chemical sediments that precipitate in water bodies, are solely products of their sedimentary environment. That is, their component minerals originated and were deposited in the same place. Other sediments originate far from the site where they accumulate and are transported from their source by some combination of gravity, water, wind, and ice. At any given time, the geographic setting and environmental conditions of a sedimentary environment determine the nature of the sediments that accumulate. Geologists carefully study the sediments in present-day depositional environments because the features they find can also be observed in ancient sedimentary rocks. Geologists apply a thorough knowledge of present-day conditions to reconstruct the ancient environments and geographic relationships of an area at the time particular sedimentary layers were deposited. This process is an excellent example of applying a fundamental principle of modern geology: the present is the key to the past. Such analyses often lead to the creation of maps depicting the past geographic distribution of land and sea, mountains and river valleys, deserts and glaciers, and other environments of deposition. Did you know? These terms are often used when describing the mineral makeup of sedimentary rocks. Siliceous rocks contain abundant quartz, argillaceous rocks are clay-rich, and carbonate rocks contain calcite or dolomite. Sedimentary environments are commonly placed into one of three broad categories: continental, marine, or transitional. Each category includes many specific sub-environments. Figure 7.23 includes an idealized diagram illustrating a number of important sedimentary environments associated with each category. Realize that this is just a sampling of the great diversity of depositional environments. Chapters 13 through 17 examine many of these environments in greater detail. Each environment is characterized by certain physical, chemical, and biological conditions. Because sediments contain clues about the environment in which they were deposited, sedimentary rocks are important in the interpretation of Earth history. A number of important examples are represented in this idealized diagram. Figure 7.23 Sedimentary environments. Figure 7.23 Full alternative text description. Sedimentary facies. When we study a series of sedimentary layers, we can see the successive changes in environmental conditions that occurred at a particular place with the passage of time. Changes in past environments may also be seen when a single layer of sedimentary rock is traced laterally. This is true because at any one time, many different depositional environments can exist over a broad area. For example, when sand is accumulating in a beach environment, finer muds are often being deposited in quieter offshore waters. Still farther out, perhaps in a zone where biological activity is high and land-derived sediments are scarce, the deposits consist largely of the calcite-rich remains of small organisms. In this example, different sediments are accumulating adjacent to one another at the same time. Different parts of each layer possess a distinctive set of characteristics that reflect the conditions in a particular environment. The term facies is used to describe such sets of sediments. When a sedimentary layer is examined in cross-section from one end to the other, each facies grades laterally into another that formed at the same time but that exhibits different characteristics. The merging of adjacent facies tends to be a gradual transition rather than a sharp boundary, but abrupt changes do sometimes occur. When a sedimentary layer is traced laterally, we may find that it is made up of several different rock types. This occurs because many sedimentary environments can exist at the same time over a broad area. The term facies is used to describe such sets of sedimentary rocks. Each facies grades laterally into another that formed at the same time but in a different environment. Smart Figure 7.24 Lateral change. Sedimentary structures. In addition to variations in grain size, mineral composition, and texture, sediments exhibit a variety of structures that are often preserved when they change to sedimentary rock. Some, such as graded beds, are created when sediments are accumulating and are a reflection of the transporting medium. Others, such as mud cracks, form after the materials have been deposited and result from processes occurring in the environment. When present, sedimentary structures provide additional information that can be useful in interpreting Earth's history. Watch tutorial, Sedimentary facies. Sedimentary rocks form as layer upon layer of sediment accumulates in various depositional environments. These layers, called strata, or beds, are probably the single most common and characteristic feature of sedimentary rocks. Each stratum is unique. It may be a coarse sandstone, a fossil-rich limestone, a black shale, and so on. When you look at Figure 7.25, or look back at the chapter opening photo and at Figures 7.1 and 7.5, you see many such layers, each different from the others. The variations in texture, composition, and thickness reflect the different conditions under which each layer was deposited. This outcrop of sedimentary strata illustrates the characteristic layering of this group of rocks. These strata are exposed at Dunraven Bay along the coast of Wales. Figure 7.25 layers are called strata. Beds range from microscopically thin to tens of meters thick. Separating these strata are bedding planes, relatively flat surfaces along which rocks tend to separate or break. Changes in the grain size or in the composition of the sediment being deposited can create bedding planes. Pauses in deposition can also lead to layering because chances are slight that newly deposited material will be exactly the same as previously deposited sediment. Generally, each bedding plane marks the end of one episode of sedimentation and the beginning of another. Because sediments usually accumulate as particles that settle from a fluid, most strata are originally deposited as horizontal layers. There are circumstances, however, when sediments do not accumulate in horizontal beds. Sometimes when a bed of sedimentary rock is examined, we see layers within it that are inclined to the horizontal. This is called cross-bedding, and it is most characteristic of sand dunes, river deltas, and certain stream channel deposits. Sand dunes typically exhibit thin layers inclined at an angle to the main bedding. Figure 7.26 Cross-bedding. Figure 7.26 Full alternative text description. Figure 7.8 to 1 full alternative text description. Graded beds are another special type of bedding. In this case, the particles within a single sedimentary layer gradually change from coarse at the bottom to fine at the top. Graded beds are most characteristic of rapid deposition from water containing sediment of varying sizes. When a current experiences a rapid energy loss, the largest particles settle first, followed by successively smaller grains. The deposition of a graded bed is most often associated with a turbidity current, a mass of sediment-choked water that is denser than clear water and that moves downslope along the bottom of a lake or an ocean. Figure 7.27. A graded bed is characterized by a decrease in sediment size from bottom to top. Graded beds are associated with submarine currents known as turbidity currents. Figure 7.27 full alternative text description. Geologists can deduce quite a bit about past environments by examining sedimentary rocks. A conglomerate, for example, may indicate a high-energy environment, such as a surf zone or rushing stream, where only coarse materials remain and finer particles are kept suspended. If the rock is arkose, it may signify a dry climate, where little chemical alteration of feldspar is possible. Carbonaceous shale is a sign of a low-energy, organic-rich environment, such as a swamp or lagoon. Figure 7.27 Graded bedding. Other features found in some sedimentary rocks also give clues to past environments. Ripple marks are such a feature. Ripple marks are small waves of sand that develop on the surface of a sediment layer through the action of moving water or air. The ridges form at right angles to the direction of motion. If the ripple marks are formed by air or water moving in essentially one direction, they will be asymmetrical, with a steeper side in the down-current direction and a more gradual slope on the upcurrent side. A stream flowing across a sandy bed and wind blowing over a sand dune produce current ripples. When present in solid rock, they reveal the direction of ancient wind or water currents. Ripple marks that form in response to the back-and-forth movement of waves in nearshore environments are symmetrical and are called oscillation ripple marks. These current ripple marks formed in sandy sediment and are now preserved in rock. B. When muddy sediments dry out, they shrink and create cracks. When the sediment is turned into rock, the mud cracks are preserved. Figure 7.28 Frozen in stone. Mud cracks indicate that the sediment in which they were formed was alternately wet and dry. When exposed to air, wet mud dries out and shrinks, producing cracks. Mud cracks are associated with environments such as tidal flats, shallow lakes, and desert basins. Fossils, the remains or traces of prehistoric life, are important inclusions in sediment and sedimentary rocks. They are helpful tools for interpreting the geologic past. Knowing the nature of the life forms that existed at a particular time helps researchers understand past environmental conditions. Further, fossils are important time indicators and play a key role in correlating rocks of similar ages that are from different places. Fossils are discussed further in Chapter 18. Concept Checks 7.7. 1. What are the three broad categories of sedimentary environments? List a specific example associated with each category. 2. Why might a single sedimentary layer include different types of rock? What term applies to the different parts of such a layer? 3. What is the single most characteristic feature of sedimentary rocks? 4. What is the difference between cross-bedding and graded bedding? 5. How might mud cracks and ripple marks be useful clues about the geologic past? For more on this idea, see Section 1.2 in Chapter 1. 7.8 Resources from sedimentary rocks. Distinguish between the two broad groups of non-metallic mineral resources. Discuss the three important fossil fuels associated with sedimentary rocks. In addition to the fact that sedimentary rocks contain critical information about Earth's history, this group is economically important as well. Sedimentary rocks are associated with important mineral and energy resources. Did you know? Producing 1 ton of steel requires about 1/3 ton of limestone and between 2 and 20 pounds of fluorspar. Non-metallic mineral resources. Earth materials that are not used as fuels or processed for the metals they contain are referred to as non-metallic mineral resources. Realize that use of the word mineral is very broad in this economic context and is quite different from the geologist's strict definition of mineral found in Chapter 3. Non-metallic mineral resources are extracted and processed either for the non-metallic elements they contain or for the physical and chemical properties they possess. Although these resources have diverse origins, many are sediments or sedimentary rocks. Because a large percentage of these materials are used in manufacturing or to make fertilizers, processes we rarely see, their importance is easy to underestimate. Table 7.1 Uses of non-metallic minerals. Table 7.1 Full alternative text description. The quantities of non-metallic minerals used each year are enormous. Per capita consumption of non-fuel resources in the United States is nearly 11 metric tons, of which more than 94% are non-metallic minerals. Non-metallic mineral resources are commonly divided into 2 broad groups: building materials and industrial minerals. Some substances fall into both groups. Limestone, perhaps the most versatile and widely used rock of all, is the best example. As a building material, it is used not only as crushed rock and building stone but also in making cement. As an industrial mineral, limestone is an ingredient in the manufacture of steel and is used in agriculture to neutralize acidic soils. Limestone is considered both a building material and an industrial mineral. This quarry is near Amsterdam, Indiana. Figure 7.29 Limestone Quarry. Building materials also include cut stone, aggregate, gypsum for plaster and wallboard, clay for tile and bricks, and cement, which is made from limestone and shale. Cement and aggregate go into the making of concrete, a material that is essential to practically all construction. Did you know? Just 2 kilometers of 4-lane highway require more than 85,000 tons of aggregate. The United States produces about 2 billion tons of aggregate per year. This represents about 1/2 of the entire non-energy mining volume in the country. A wide variety of resources are classified as industrial minerals. Some are sources of elements or compounds that are used in the manufacture of chemicals and the production of fertilizers. Corundum and garnet are used as abrasives. Deposits of industrial minerals are generally far more restricted in distribution and extent than are deposits of building materials. Energy resources. Earth's tremendous industrialization over the past 2 centuries has been fueled, and is still fueled, by burning coal, petroleum, and natural gas. About 81% of the energy consumed in the United States today comes from these basic sources. Figure 7.30 shows where our energy comes from and what it is used for. Our reliance on fossil fuels is obvious. Although we are using greater quantities of energy from alternative sources such as solar, wind, geothermal, and hydroelectric, the U.S. Department of Energy projects that fossil fuels will continue to be very important for decades to come. The total was 98.3 quadrillion BTU. A quadrillion is 10 raised to the 15th power, or a million billion. A quadrillion BTU is a convenient unit for referring to U.S. energy use as a whole. Smart Figure 7.30 U.S. energy consumption, 2014. Smart Figure 7.30 Full alternative text description. Coal. Watch tutorial, U.S. energy consumption. In addition to oil and natural gas, coal is commonly called a fossil fuel. This designation is appropriate because when coal is burned, energy from the sun that was stored by plants many millions of years ago is being used, hence the actual burning of fossils. In the United States, coal fields are widespread and contain supplies that should last for hundreds of years. Production is shown in millions of tons produced in 2014. The percentage of the total production is indicated in parentheses. Most of the coal mined in the United States is subbituminous and bituminous. Figure 7.31 Full alternative text description. Figure 7.31 Coal fields of the United States. Coal is plentiful, but its recovery and use present a number of challenges. Surface mining can turn the countryside into a scarred wasteland if careful. Reclamation is not carried out to restore the land. Today, all U.S. surface mines are required to reclaim the land. Although underground mining does not scar the landscape to the same degree, it has been costly in terms of human life and health. Strong federal safety regulations have made U.S. mining quite safe. However, collapsing roofs, gas explosions, and the required heavy equipment remain hazards. Over the years, the share of coal produced from surface mines has increased significantly, from 51% in 1949 to about 65% in 2014. Burning coal produces emissions that adversely affect the environment and human health. Principal emissions resulting from coal combustion include the following: sulfur dioxide, which contributes to acid rain and respiratory illnesses. Nitrogen oxides, which contribute to smog and respiratory illnesses. Particulate matter, which contributes to smog, haze, respiratory illnesses, and lung disease. Carbon dioxide, the primary greenhouse gas produced from the burning of fossil fuels, which plays a significant role in the heating of our atmosphere. The coal industry has found several ways to reduce sulfur, nitrogen oxides, and other impurities from coal and has developed more effective ways of cleaning coal after it is mined. Coal consumers have shifted toward greater use of less polluting low-sulfur coal. Yet significant challenges remain. Did you know? Wyoming is far and away the largest producer of coal in the United States. With 39.4% of U.S. production in 2014, Wyoming is home to the 8 largest mines in the country. More than 90% of the coal produced in the United States is used for the generation of electricity. Coal accounted for about 42% of U.S. electric power in 2014. Oil and natural gas. Together, oil and natural gas provided more than 60% of the energy consumed in the United States in 2014. By examining Figure 7.30, you can see that the transportation sector of the U.S. economy relies almost totally on petroleum as an energy source. In 2011, natural gas surpassed coal for the first time in more than 30 years as a source of energy in the United States. An important reason for this is the use of new technologies that have increased production from shale formations. Users of natural gas are almost evenly divided among the 3 categories other than transportation in Figure 7.30. Like coal, petroleum and natural gas are biological products derived from the remains of organisms. However, while coal formed mostly from plant material that accumulated in swampy environments on land, as shown in Figure 7.18, oil and natural gas originated mainly from microscopic marine plankton in ancient seas millions of years ago. This organic material accumulated in marine sedimentary basins together with mud, sand, and other sediments that protected it from oxidation. With increased temperature and burial, chemical reactions gradually transformed this organic matter into the liquid and gaseous hydrocarbons we call petroleum and natural gas. Unlike the organic matter from which they form, petroleum and natural gas are mobile. These fluids are gradually squeezed from the compacting, mud-rich layers where they originate, called the source rock, into adjacent permeable beds such as sandstone, where openings between sediment grains are larger. Because this occurs in a marine environment, the rock layers containing the oil and gas are saturated with salt water. Oil and gas, being less dense than water, migrate upward through the water-filled pore spaces of the enclosing rocks. A geologic environment that allows for economically significant amounts of oil and gas to accumulate underground is termed an oil trap. Several geologic structures can act as oil traps, and all have two basic features: a porous, permeable reservoir rock that can yield petroleum and natural gas in sufficient quantities to make drilling worthwhile, and a cap rock, such as shale, that is virtually impermeable to oil and gas and hence traps them in the reservoir rock. Figure 7.32 illustrates the following common oil and natural gas traps. Smart Figure 7.32 Full alternative text description. Anticline. One of the simplest traps is an anticline, an uparched series of sedimentary strata. The rising oil and gas collect at the top of the fold. Because of its lower density, natural gas collects above the oil. Both the oil and gas rest on the denser water that saturates the reservoir rock. Smart Figure 7.32 Common oil traps. Watch tutorial, Oil traps. Fault trap. When strata are displaced so that a dipping reservoir rock abuts an impermeable bed, a fault trap forms, as shown in Figure 7.32b. The upward migration of the oil and gas is halted where they encounter the fault. Salt dome. In the Gulf Coastal Plain region of the United States, important accumulations of oil occur in association with salt domes. Such areas have thick accumulations of sedimentary strata that include layers of rock salt. Salt occurring at great depths has been forced to rise in columns by the pressure of overlying beds. These rising salt columns gradually deform the overlying strata. Because oil and gas migrate to the highest level possible, they accumulate in the upturned sandstone beds adjacent to the salt column. Stratigraphic trap. A stratigraphic trap results primarily from the original pattern of sedimentation rather than from structural deformation. The stratigraphic trap illustrated in Figure 7.32d exists because a sloping bed of sandstone thins to the point of disappearance. Whatever the type of trap, when drilling punctures the lid created by the cap rock, the oil and natural gas, which are under pressure, migrate from the pore spaces of the reservoir rock to the drill pipe. On rare occasions, when fluid pressure is great, it may force oil up the drill hole to the surface, causing a gusher at the surface. Usually, however, a pump is required to extract the oil. Hydraulic fracturing. Some shale deposits contain significant reserves of oil and natural gas that cannot naturally leave because of the rock's low permeability. The practice of hydraulic fracturing shatters the shale, opening up cracks through which the oil and natural gas can flow into wells and then be brought to the surface. Figure 7.33 illustrates the process. The fracturing of the shale is initiated by pumping fluids into the rock at very high pressures. The fluid is mostly water but also includes other chemicals that aid in the fracturing process. Some of these chemicals may be toxic, and there are concerns about fracking fluids leaking into freshwater aquifers that supply drinking water. The injection fluid also includes sand, so once fractures open up in the shale, the sand grains can keep them propped open and permit the oil and gas to continue to flow. Once the fracturing has been accomplished, the fracking fluid is brought back to the surface. Often this wastewater is injected into deep disposal wells. In some locations, these injections appear to trigger numerous minor earthquakes. Due to concerns about potential groundwater contamination and induced seismicity, hydraulic fracturing remains a controversial practice. Its environmental effects remain a focus of continuing research. Did you know? The first successful oil well was completed by Edwin Drake on August 27, 1859, along Oil Creek near Titusville, Pennsylvania. Oil-bearing strata were encountered at a depth of just 20.7 m. This well stimulation process is commonly used in low permeability rocks such as shale to increase oil and/or natural gas production. Figure 7.33 Full alternative text description. Concept checks 7.8. Figure 7.33 Hydraulic fracturing. 1. Non-metallic mineral resources are commonly divided into what two broad groups? Give some examples of materials that belong to each group. 2. Why are coal, oil, and natural gas called fossil fuels? What part of U.S. energy consumption does each represent? 3. Coal has the advantage of being plentiful. What are some of coal's disadvantages? 4. What is an oil trap? Sketch and label two examples. What do all oil traps have in common? 5. Describe the circumstances in which hydraulic fracturing is used. 7.9 The carbon cycle and sedimentary rocks. Relate weathering processes and sedimentary rocks to the carbon cycle. To illustrate the movement of material and energy among the spheres of the Earth system, let us take a brief look at the carbon cycle. Most carbon is bonded chemically to other elements to form compounds such as carbon dioxide, calcium carbonate, and the hydrocarbons found in coal and petroleum. Carbon is also the basic building block of life, as it readily combines with hydrogen and oxygen to form the fundamental organic compounds that compose living things. Figure 7.34 Carbon cycle. This simplified diagram emphasizes the flow of carbon between the atmosphere and the hydrosphere, geosphere, and biosphere. The arrows show whether the flow of carbon is into or out of the atmosphere. Figure 7.34 Full alternative text description. Certainly one of the most active parts of the carbon cycle is the movement of CO2 from the atmosphere to the biosphere and back again. In the atmosphere, carbon is found mainly as carbon dioxide. Atmospheric carbon dioxide is significant because it is a greenhouse gas, which means it is an efficient absorber of energy emitted by Earth and thus influences the heating of the atmosphere, a process described in more detail in Chapter 20. Because many of the processes that operate on Earth involve carbon dioxide, this gas is constantly moving into and out of the atmosphere. Through the process of photosynthesis, plants absorb carbon dioxide from the atmosphere to produce the essential organic compounds needed for growth. Animals that consume these plants use these organic compounds as a source of energy and, through the process of respiration, return carbon dioxide to the atmosphere. Further, when plants die and decay or are burned, this biomass is oxidized, and carbon dioxide is returned to the atmosphere. In the oceans, photosynthetic plankton plays the same role that plants do on land. Not all plants decay immediately back to carbon dioxide. A small percentage is deposited as sediment. Over long spans of geologic time, considerable biomass is buried with sediment. Under the right conditions, some of these carbon-rich deposits are converted to fossil fuels, coal, petroleum, or natural gas. Some of these fuels are eventually recovered and burned to generate electricity and fuel our transportation system. One result of fossil fuel combustion is the release of huge quantities of carbon dioxide back into the atmosphere. Carbon also moves from the geosphere and hydrosphere to the atmosphere and back again. For example, volcanic activity early in Earth's history is thought to have been the source of much of our atmosphere's carbon dioxide. One way that carbon dioxide makes its way back to the hydrosphere and then to the solid Earth is by first combining with water to form carbonic acid, which then attacks the rocks that compose Earth's crust. One product of this chemical weathering of solid rock is the soluble bicarbonate ion, which is carried by groundwater and streams to the ocean. Water-dwelling organisms extract this dissolved material to produce hard parts of calcium carbonate. When the organisms die, these skeletal remains settle to the ocean floor as biochemical sediment and become sedimentary rock. In fact, the crust is by far Earth's largest depository of carbon, where it is a constituent of a variety of rocks, the most abundant being limestone. When the rock is carried to great depths at a subduction zone, where metamorphism and melting can occur, the heated rock recombines into silicate minerals, releasing carbon dioxide. When volcanoes erupt, they vent the gas to the atmosphere and cover the land with fresh silicate rock, beginning the cycle again. In summary, carbon moves among all four of Earth's major spheres. It is essential to every living thing in the biosphere. In the atmosphere, carbon dioxide is an important greenhouse gas. In the hydrosphere, carbon dioxide is dissolved in lakes, rivers, and the ocean. In the geosphere, carbon is contained in carbonate sediments and sedimentary rocks and is stored as organic matter dispersed through sedimentary rocks and as deposits of coal and petroleum. Concept checks 7.9. 1. Describe how chemical weathering and the formation of biochemical sediment remove carbon from the atmosphere and store it in the geosphere. 2. Provide an example of carbon moving from the geosphere to the atmosphere. Concepts in review: sedimentary rocks. 7.1 An introduction to sedimentary rocks. Explain the importance of sedimentary rocks and summarize the part of the rock cycle that pertains to sediments and sedimentary rocks. List the 3 categories of sedimentary rocks. Key terms: sedimentary rock, detrital sedimentary rock, chemical sedimentary rock, organic sedimentary rock. Though igneous and metamorphic rocks make up most of Earth's crust by volume, sediment and sedimentary rocks are concentrated near the surface. There, at the interface of Earth's 4 spheres, sediments and the rock layers, they eventually form record past conditions and events at the surface. Sedimentary rocks contain fossils that show the evolution of life over time. Numerous geologic resources are primarily associated with sedimentary rocks. Examples include coal, oil, uranium, and several major ores of metals. Sediments are the raw materials from which sedimentary rocks are made. Sediments are produced from the weathering of pre-existing rocks. Both solid particles of many sizes and chemical residues, including the ions in solution, qualify as sediments. Once produced, sediments are transported from their source area by water currents, wind, glacial ice, or simply downhill under the influence of gravity. Eventually, solid particles are deposited at a new site where they are compacted and/or cemented into a detrital sedimentary rock. Ions in solution are precipitated and become the raw material for chemical sedimentary rocks. There are 3 main varieties of sedimentary rocks: detrital, chemical, and organic. Of the 2 main sources of energy that drive the rock cycle, Earth's internal heat and solar energy, which one is primarily responsible for the formation of sediment and sedimentary rocks? Briefly explain. 7.2 Detrital sedimentary rocks. Describe the primary basis for distinguishing among detrital rocks and discuss how the origin and history of such rocks might be determined. Key terms: shale facility, sandstone sorting conglomerate, breccia. Detrital sedimentary rocks are made of solid particles, mostly quartz grains and microscopic clay minerals. Quartz and clay dominate because, unlike most other minerals, they are stable at Earth's surface. Feldspars and micas are conspicuous additions to certain detrital sediments, indicating a relatively short time in the chemical weathering environment. These were mechanically weathered, transported a relatively short distance, and deposited with minimal decomposition. Detrital sedimentary rocks are classified mainly based on the size of the sedimentary grains of which they are composed. Grain size is a clue about how energetic the environment of deposition was. Bigger particles indicate more powerful transporting currents. Finer grains can be deposited only where current energy is relatively low. Shale is made mostly of small grains of clay minerals that accumulate in low-energy depositional environments such as the deep sea, lake bottoms, and floodplains adjacent to rivers. Shale exhibits facility due to the alignment of microscopic clay flakes parallel to bedding. Shale containing a lot of organic material forms in low oxygen environments and is characterized by a black color. Sandstone is dominated by sand-sized grains and may exhibit various degrees of sorting. Sorting is a reflection of how abruptly or gradually the sand was deposited. Rounding of the individual sand grains is another important aspect of a sandstone's texture. Rounder grains signify further transport, while angular grains imply a shorter transport distance. Sandstones also vary in their composition. The presence of minerals that are relatively unstable at the surface implies that the sand did not undergo much chemical weathering prior to deposition. The greater the proportion of quartz, the more the source sediment was chemically weathered before deposition. Three main varieties of sandstone worth knowing are quartz sandstone, arkose, and greywacke. Conglomerate and breccia are characterized by a high proportion of gravel-sized grains if deposited by water. A conglomerate implies a very energetic current.